All right, this is our last lesson. And we'll discuss some very neat things that happen when we consider waves, or two different kinds of waves, or actually the two different waves that are interacting. And that's what we'll see as a result, happens as a result of the principle of superposition. So we can have things called interference or beating pattern between the waves, or standing waves. So the goals of this lesson are to see how superposition of waves creates these kinds of phenomena, beats, interference, standing waves, how we can still use the wave equation to solve for the components of the individual waves and the parameters of their superposition, and to then figure out what these harmonic frequencies are, what these things called harmonic frequencies are, for example, on guitars or string instruments, and how they form on standing waves. So we'll start again with our wave equation, which we introduced last lesson. The wave equation is a linear equation. This is because the variable z and its derivative are only appearing linearly. They don't come in squared to some power in the equation. And an important property of linear equations is that you can superpose them. So if you have two linear equations, z1 and z2 as a function of position and time, then their sum, z1 plus z2, will also be a solution to the wave equation. So if each of these is a solution to the wave equation, their sum will also be a solution of the wave equation. And this is the principle of linear superposition. So let's take a quick example here. Say we have, this is one of our waves, and this is the second one of our waves. They have all different properties, wavelengths, periods. Then the sum of these two waves will be given by this. It's actually also a wave that can exist on a string. And let's show a simulation here. Here is one wave, a certain period. Here's a different wave, a different period, different amplitude, and you can actually sum these up. And this is what the resulting wave will look like. And you see it has elements both of the low frequency wave and of the high frequency wave, and how it looks. So the bottom line here is that if we superpose two or more waves, then the displacement of the resulting wave is the sum of the displacements from the individual waves. And if both displacements, say, are positive at a given point, then the result will be even bigger than individual displacements. And this is called constructive interference. Whereas if the displacements have opposite signs, one is positive, one is negative, then the net displacement will be the average, or it can actually completely cancel out, in which case we have destructive interference. And let's use graph examples to demonstrate this again. Here are two waves that have exactly the same period and are completely in phase, so their peaks always align. So when you add these up, the resulting wave has a bigger amplitude still, equal to the amplitude of A plus B. Here is the same wave as in the first example, but now the second wave has been shifted in phase by pi over 2. So now what happened? It's been shifted in phase by a factor of by a phase of pi. Sorry, not pi over 2. So then now what happens is that the peaks and the troughs align. So when you add these up, you actually get no wave at all, even though you may have had waves that you were initially adding up. So these are examples of constructive interference and destructive interference, but you can have any sort of scenario in between, which will then create something intermediate between destructive and constructive interference. So now let's take a look at an example. We have two sinusoidal waves that have the same frequency, wave number, amplitude, but they have a phase difference. So let's see what their superposition looks like, and show that it actually also satisfied the wave equation. Looks like a simple harmonic wave, but let's see what the amplitude of this new wave is. So here's our solution. Here are our two waves. We're told they have the same amplitude, same wavelength, same frequency, so I've kept these parameters here the same, A, K, omega. but they have different phases. So now let's add them up. So the resulting wave is just y as a function of x and t. It's the sum of the individual ones. And here I've just written out the sum of these two waves, and I've actually used a substitution. Instead of writing kx minus omega t in each case, I've just set kx minus omega t equal to this parameter theta. So the sum is actually just a times cos theta plus phi 1 plus cos theta plus phi 2, where theta is this factor here. So this is just for ease of work in this case. So now we have a sum of cosines, and there's a trigonometric identity that allows us to rewrite that as 2 times the amplitude times a cosine of the two arguments added divided by 2 times the cosine of the two arguments subtracted from each other, again divided by 2. So this is a trigonometric identity. So now we simplify things here a little bit. We get 2a times cosine of theta, because we have two thetas here, plus phi 1 plus phi 2 over 2, times cosine of phi 1 minus phi 2, the thetas cancel, over 2. So here's what we see now. This factor here still has theta. So this is still dependent on x and time. But the other factor here is only a cosine of the phase difference over 2, and these actually are non-dependent with position or time, they're constant. So now we see that we get a resulting wave, the sum of the two waves, is still a simple harmonic wave because it still has this kx minus omega t dependence under the cosine. It has a phase that is the half of the phase sum of the two waves, but it has a modified amplitude. That's 2a times cosine of the phase difference over 2. So the resulting wave is also satisfies the wave equation as a simple harmonic wave, but with a modified amplitude and a phase that's determined by the half sum of the two phases. So this is one example of interference. Let's take a look at a few examples. Actually, a very neat one is interference created by two individual sources here, say on the surface of a water tank. And what you have is light shining through, so you can actually see the ripples. And depending on exactly how far you are from both sources, you can have either rays of destructive interference, where the two wave amplitudes will cancel out and there'll be very little oscillation, or you can have regions of constructive interference that are right in between those regions of destructive interference, where the amplitudes add up. So you have very high peaks and very deep troughs. The troughs here are the black regions. So you can see, and this is actually determined exactly based on how far from both sources you are at any given location. So when the oscillations are in phase, you have constructive interference, and when they're exactly out of phase, you'll have destructive interference on the surface. Another very neat result of wave superposition is the so-called beat phenomenon. And it's called a beat because it has a regular frequency to it, even though it's not necessarily exactly what you may think of when you're thinking of a drum beat. But beats are the result of the superposition of two waves with slightly different frequencies. So what happens then is that because the frequencies are only slightly different, there are some times when the two waves will add constructively, so you get a higher oscillation, and then sometimes it will just completely cancel out, so you get a very little amount of oscillation. So you're switching between constructive and destructive interference in the beat phenomenon. So if the waves, for example, are sound waves, what this means is that when you have constructive interference at higher amplitude, you hear a louder sound, you hear more power. And when you have destructive interference, the sound gets softer, so you hear it less. So they're also important for radio transmission or for tuning musical instruments, because that's how you can actually tell whether two musical instruments are in tune when the beat pattern has vanished. For measuring frequencies and vice versa. So here's how the creation of a beat frequency works. Here we have two slightly different waves. The top one has 20 oscillations in these 25 seconds. So it has a frequency of 0.8 hertz. The bottom one has two more oscillations, 22 oscillations in 25 seconds, so its frequency is 0.88 hertz. So what happens now when we add these two together? In the beginning, when they're completely in phase, their amplitudes add up, so we have a wide oscillation, but then after a little while they start to be out of phase. So here they're destructively interfering, and then again you have this increasing amplitude and decreasing amplitude. This is now the beat pattern. And as you can see, the beat pattern itself repeats. So there's a certain time between two consecutive times when you have maximum oscillation. So there's a frequency to the beat pattern itself. And let's see how to determine that beat frequency now. So here are our two waves. And so here's our superposition, which is the sum of these two waves. So what we then do when we sum these up, this is just a rewrite of this line here. Again, we use that same trig identity that we had before. So we get a wave that has two sets of frequencies in it. One is a high frequency, which we call the signal of the information carrier, and one is a low frequency, which is the difference between the two initial frequencies. So we call this one the information carrier, but this is actually the modulation frequency. So now when these two frequencies become very similar, then we have this beat phenomenon. And we call that frequency, the difference of the two divided by 2, the frequency of the beat itself. And I'm going to have a video playing up here, which is why this placeholder just showed up. So with sound waves, again, what we hear is proportional to the amplitude of the oscillation. And that's because the energy of carried by the sound itself is proportional to the square of the amplitude. So actually what we hear is really proportional to the square of the amplitude, not to the amplitude itself. And then the modulation frequency is f1 minus f2 over 2. But because what we're seeing is the square of the amplitude, we actually end up hearing something that's twice the oscillation of the beat frequency, because for every peak we hear an increase in amplitude, and for every trough we also hear an increase in amplitude because we're squaring the amplitude. So the audible beat frequency is actually just f1 minus f2 as opposed to f1 minus f2 over 2, which is the actual beat frequency. So let's hear what this actually happens. We'll show two tuning forks that have slightly different frequencies, and you'll hear, let me make sure that I have my audio loud here, so you should be able to hear the beating of the two frequencies. This is a neat demo from St. Mary's University. So you saw the tuning forks they were tuned to slightly different frequencies, and at the end the beating that we heard was this 1 1 1 1 1 1, the change in volume. So that was the beating of the frequencies of the two tuning forks together. All right, let's take a different solution. Let's consider a guitar. So two guitar strings are in tune when they have this frequency, 414 hertz. This is in the audible range. So now we tighten one slightly, and we know that this actually is going to, intuitively, we know it's going to increase the frequency of the guitar string. So now the frequency becomes a little higher for that one string. We play them both, and we hear a beat frequency, this 1 1 1 1 1, which is occurring 4 times a second, so 4 hertz. So what is the frequency of the tightened string when the original string had a frequency of 414 hertz? So here's our solution. We have the audible volume modulation, and that, as we already explained, happens at twice the actual beat frequency. And the beat frequency is f1 minus f2 over 2. So then the audible modulation that we hear actually happens at a frequency twice that, so that's just f1 minus f2. And we're told that the frequency of that audible modulation is 4 hertz. So f1 minus f2 is 4 hertz. And now, because the string that is tightened has a higher frequency, that's the string that will have frequency f1, and the original frequency will be f2. So then we can figure out that the frequency of a tightened string is slightly higher, and it's going to be 4 plus 414, which equals 418 hertz. So let's look at strings a little bit more. You know that when you pluck a guitar string, the string will just oscillate back and forth, and the middle of the string oscillates the most, whereas at the two ends where the string is attached, you have no oscillation. So it's the frequency of the vibration of the string that will tell you what note you're playing on, or what tone you're playing on the guitar. Even though there doesn't appear to be any motion from one end of the string to the other, this is still a transverse wave. It doesn't move, however. And what happens here is that the transverse wave actually gets constantly reflected from one end to the other. And we also know, in fact, that we could also excite harmonics on the guitar string, so not just have a single oscillation across the string, but maybe 2 oscillations across the string. And this happens, say, if you were to pluck the string but you touch it right in the middle, so then you actually get the full, without depressing, just touching in the middle, you get the full oscillation of the string, but you also get a second set of oscillations that actually have half the wavelength or twice the frequency. So you can actually get a different kind of sound from the same string if you were to do that. So what about these standing waves? How do we describe these mathematically? So we know, again, the displacement oscillates periodically with time. So it must be something like cosine omega t. There's no x displacement. And we know that we have the length of the guitar string. The string is fixed at both ends. So the displacement z at both x equals 0 and x equal the length of the string should be 0. This is what corresponds to the boundary conditions at the ends of the string. The vertical displacement, or the displacement z should be 0. So if our equation is something like this, zx equals a cosine omega t times sine x, we can convince ourselves that this part here will satisfy the condition that when x is equal 0, z is also going to be 0. So our equation looks something like this for a standing wave on a guitar string. We still have the other boundary condition to satisfy, that the displacement, the vertical displacement, should be also 0 when x equals L. So this should be 0 when x equals L. So this will only happen for certain values of k, as we'll see. So the sine of KL should be 0 for the other end of the string to be attached. So that means that that means that the sine itself should be either pi or 2 pi, or 3 pi or 4 pi, and so forth. So k should be either pi over L, which will make the sine equal, the argument of the sine be pi, so the sine will be 0. Or k should be 2 pi over L, which will make the argument of the sine 2 pi, and again the sine will be 0. Or k will be 3 pi over L, which will make the argument of sine 3 pi, so any multiple of pi, the sine will be 0. So in general, the wave number should be some integer times pi over L to have a standing wave on a spring. So then we can put this solution from the boundary condition into our expression for the standing wave, and we get that this is our general form for a standing wave on a string. A cosine omega t, so it oscillates with time, sine n, where n is an integer, 1, 2, 3, and so forth, times pi x over L. So then this means that the allowable values of the wavelength of a standing wave on a string are then only, so wavelength being lambda and being 2 pi over k, where k is now n pi over L. So we can have wavelengths that are only certain values, and they correspond to twice the string length over n. And n has to be 1, 2, 3, or 4. 1, 2, 3, or so forth. So here's what this looks like. So here is our string oscillating back and forth at the longest possible wavelength, which is actually half the string length because we're seeing only one amplitude across the string. So in this case, n equal 1, we call this the first harmonic or the fundamental frequency of the string. So, and then the wavelength is actually twice the length of the string. Here is a full wavelength across the string, so lambda is equal to L. So this is where n equals 2, and this is what we call the second harmonic. You can have 3 oscillations or 1.5 wavelengths, so this is for n equal 3, or 4, so 2 full wavelengths on the string, so n equal 4, and this will be the fourth harmonic. So these are what are called harmonics on strings. And for the string here, you have a node where the displacement is always 0, or antinodes where the displacement is always maximum, where the where the displacement will peak. It's not necessarily always maximum because it goes back and forth, but that's where the displacement will peak at the antinodes. So we know that the speed of a wave is omega over k, or in the case of a string, is the square root of a tension over mu. So this is the speed of a traveling wave, and we can actually use the same expression for a standing wave, even though the wave does not actually move, and we'll see in a little bit why that's the case. So if we solve for the frequency, we get that the angular frequency is 2 pi f. That's k times the square root of t over mu. So then we can find an expression for the frequency. Is k over 2 pi times square root of t over mu. And then k we can express as 2 pi over lambda. So then we have 1 over lambda times square root of t over mu. And we know this is a standing wave on a string, so the wavelengths are only a certain sets of numbers that correspond to 2L over n. So then our expression for a frequency or any harmonic frequency on a string is n, where n is an integer, over 2L times square root of t over mu. And if you have played a musical instrument like a string instrument, you actually know that you intuitively know this is a correct equation. You know that if the string is tightened, the frequency will increase, it'll become higher pitch. If the string is heavier, its frequency will be lower. It'll have lower pitch, so heavier or thicker. If the string is longer, under the same tension and weight, the frequency will be longer. And if we're trying to excite a higher harmonic, obviously the frequency will be higher. So this corresponds to what your intuition might tell you from experience with musical instruments. So let's take an example where we apply this equation. So we have a tension on a wire of 2.8 kilonewtons. We have the length of our wire, 2.6 meters, and we know the frequency of a standing wave in the fundamental mode. So the fundamental mode is where we actually have only half a wavelength across the wire. So this is n equal 1. And the frequency is 310 hertz. Again, in the audible range. What is the mass of the wire? So let's use our expression from the previous slide, where we have the frequency equals square root of, so n over 2L times square root of t over mu. And we are given the mass, so we're trying to figure out what the mass is, but we're given what the length is. So we express mu as m over L. We're given the length, we're given the n as 1, the fundamental. We're given the frequency, F, and the tension, 2.8 kilonewtons. So then F equals this, and then after we move m to the other side, square both sides to get rid of the square root, we have this result. So the mass of the string is 2.8 grams. So this is how we use the properties of that are given by the wave equation to determine a parameter for the medium through which the wave propagates. So now let's see why the velocity is still relevant in a standing wave, even though we actually have no motion in the direction of the propagation. So standing waves are actually the superposition of two traveling waves themselves. And we have a left traveling wave and a right traveling wave, left and right moving traveling wave. And we know now that we can control the direction in which the wave moves by changing the sign in front of the argument for time. So the leftwards traveling wave has a positive sign, and the rightwards traveling wave has a negative sign. And to get a standing wave, we want to have the same amplitude, same wavelength, same frequency. So when we superpose these, we just get that the superposition, the standing wave, has an amplitude of A/2 as the individual. I'm just adding these numbers up here. So this is going to be A/2 sine this plus A/2 sine this. So then, if we actually simplify this again using trigonometric identities, we get that the result is A times, so A now twice the amplitude, times sine kx cosine omega t, which is exactly the expression that we had before for a standing wave. And here's the thing to note, there's no dependence of the form kx minus omega t, which will indicate propagation of signal along the wave. So because of this, the propagation itself is 0, even though we still have a combination of two waves that are moving in opposite direction. Now, if the two amplitudes are not exactly the same, then we don't exactly have a standing, not exactly a standing wave, because then we'll not have a perfect constructive or destructive interference at the nodes and the antinodes. So let's see how we actually get these two waves to add up together to a standing wave. So let's imagine that we have a string that's fixed on both ends. So we know that a propagation, if we jerk it on one end, it will travel to the other end. But if the other end is fixed, what happens then is that propagation will actually get reflected. So then the reflection will send the wave traveling back toward us, and the superposition of these two oscillations then, if it's driven at the appropriate frequency, will produce a standing wave. Again, only at the appropriate frequency, if we drive this oscillation at the appropriate frequency. And there's several animations and videos associated with this lesson that I very strongly encourage you to take a look at, because they demonstrate very nicely how you can get standing waves on strings that are attached to both ends. So let's take another example, and this is going to be the last example ever for the semester. So we have two traveling waves moving in opposite directions along the x-axis, and they interfere to produce a standing wave that we just talked about that has the form of z equals 6 sine kx cosine omega t, where k is 3 pi per meter, so this is the wave number, and omega is 22 pi per second. This is the angular frequency in radians per second of the combined standing wave. The question is, what are the frequencies and the speeds of the two traveling waves? And the second part is, what are the equations that describe the traveling waves themselves as opposed to the standing waves? All right, let's do it. So we know a standing wave should have this form. It should be the product of a sine and a cosine, the sine of kx cosine omega t, times some amplitude. And that should be, and this is what corresponds to this here, and that should be the superposition of two traveling waves, one that moves left and one that moves to the right. So these are our two traveling waves, and the only difference between them here is that the difference in sign in front of t, because this one is moving to the left and this one is moving to the right. So then these actually, wave number and angular frequencies are the same already as they were given to us. So then the frequencies, and we know they should be the same to produce a standing wave. So f, the frequency, is going to be omega over 2 pi. And omega, in our case, is 22 pi per second, 22 pi radians per second. So omega over 2 pi is going to be 22 hertz. And the velocity then is omega over k, the angular frequency over the wave number, and it's 7.3 meters per second. Here's our k here. And then we just put in these numbers here, and the equations for the two standing waves are going to be Z1, Z2, half the amplitude, so it's going to be 3 over here, and then sine kx plus omega t, and we are already given what k and omega are, so these are our equations for these two standing waves. And that wraps up the material that we've had for this semester, and we'll probably do a review session at some point before the final exam.